This is the pre-lab lecture for the Cobalt complexes lab in Chem 162. In the first week of this lab, you synthesize two different complexes that contain a cobalt ion surrounded by either 6 ammonia molecule ligands or 5 ammonia ligands and 1 chloride ion ligand. And then in the second week, we analyze those compounds, we take their UV visible spectra, and we relate that back to the structure of the two different complex ions. Today I want to go over 3 different aspects of this lab. One is the basics of color, which will help you understand why various compounds look the way they do. Second part of the lab is an explanation of crystal field theory, which is a model that explains why different complexes have different colors. And third is the limiting reaction calculation that you need to do for this experiment. Let's look at the basic physics of what causes substances to have color. An object appears colored if it absorbs certain wavelengths of light. It turns out that the color of the light that we see when we look at something is the complementary color of the light that it absorbs. So if you look at the color wheel that we have here, and you think about the first compound we synthesized, which is the hexamine compound, it was orange. And if something is orange, that means that it absorbs light in the complementary region of the spectrum, which would be the opposite position on the color wheel. So if we start in the middle of the orange region of the spectrum of the color wheel and draw a line straight through the center to the blue region, we'll see that that compound that appears orange is actually absorbing light in the blue region of the spectrum, somewhere around, say 450 to 500 nanometers in wavelength, somewhere on that part of the spectrum. Remember that visible light has wavelengths from somewhere around 380 or 400 nanometers to about 750 or 800 nanometers. So this wavelength 450 to 500 nanometers will be in the blue region of the spectrum. On the other hand, the second compound that we synthesized, the pentamine chloro compound, was rose colored, and that's going to be in the red region of the spectrum. And it's more towards the violet edge of the red. So we'll start here in this edge of the red. Get my pen to write in blue here. We'll start in the violet edge of the red and draw a line straight through the center of the color wheel, and we end up in the green. And if we look at the wavelengths there, that's going to be somewhere around 550 to 560 nanometers in wavelength. So those are the two compounds that we synthesized, and those are the wavelengths that we predict that they would absorb. The orange compound will be somewhere between 450 and 500 nanometers. The rose compound will be somewhere around 550 to 560 nanometers. Now, in order to verify what wavelengths of light the compounds absorb, we're going to take their UV visible spectra. And that's on the next slide. A UV visible spectrum is just a graph that shows the relative absorbance of a substance as a function of wavelength. So a spectrum is done by scanning with a spectrometer through a range of wavelengths and measuring the absorbance at each wavelength. Now you could do this with a Spec 20 like you might have used in lab before. So in that you would take your sample, you would put it in, and you would measure its absorbance at say 400 nanometers. Then adjust the spectrometer up to 410 nanometers and take another absorbance reading. Then adjust it to 420 and take another absorbance reading, and so on every 10 nanometers till you get up to the top of the spectrum at 700 nanometers. And then plot that data, and you would see a diagram that looks something like this. We could also do this on a spectrometer like the Shimadzu, which is the one we're going to use today in this lab, and in that case the spectrometer does it for us. So it'll scan the wavelengths for us and go through all of the wavelengths and take the absorbance readings and then create a plot for us. What the quantity we're interested in determining is this wavelength here, lambda max, for each of our compounds. So each of our compounds will have a different lambda max. That's the wavelength at which the maximum absorbance occurs. That symbol lambda, it looks like this, is the symbol for wavelength. And wavelength in the visible region of the electromagnetic spectrum is measured in nanometers. And so you'll see on the x-axis on our graph here, we've got wavelength in nanometers, and on the y-axis we've got absorbance. And absorbance is just measured in something called absorbance units. So this is what a spectrum looks like. And for this compound, the lambda max, or the absorbance peak, is indicated to be at 498 nanometers, which is in the green range. And if you would go back and look at the color wheel, you would see that that would be correspond to a compound that was in the red to purple color range. Okay, so let's take a look at what crystal field theory is all about. This diagram here shows a typical visible spectrum of a compound. And in this case we have, you'll see wavelength in nanometers going across the x-axis, and we have absorbance, relative absorbance, going up the y-axis. The relative absorbance is measured in absorbance units. And what this is this is just a graph showing what wavelengths of light are absorbed by a substance. And so we can see here that at 400 nanometers wavelength, the absorbance is pretty low. It starts increasing as we get up to about 500 nanometers. It drops off. There's a little bump at around 575. We call that a shoulder. And then it drops off pretty smoothly to about 700 nanometers. What we're interested in for purposes of our experiment today is the lambda max, which is the wavelength where the absorbance maximum occurs. So lambda, the symbol that looks like this, is the symbol for wavelength, and we put a little subscript max on there to indicate the maximum, the absorbance maximum, and what wavelength corresponds to that. In this picture here you can see that for this compound the absorbance maximum happens to be 498 nanometers, which is in the green range of the spectrum. That would correspond to a compound that's red in color, more in the orange to red than in the rose red range. So that's an absorbance spectrum, and that's what we're going to be doing on the Shimadzu spectrometer. The defining feature really that is the essence of science is the explanation of observations by developing models or theories. In this case, we have two similar compounds that are noticeably different in a specific property. In this case, their color, the color of light that they appear to our eye, and by inference the color of light that they absorb. And so the question arises, what is causing these compounds to have the colors they do? We just saw that the color of a substance is determined by the wavelength of light that it absorbs. So these two compounds are apparently absorbing different wavelengths of light. In order to understand how this is happening, we need to think back to the electronic structure of atoms that you looked at in Chem Prin 1. When an atom or a molecule absorbs a photon or a packet of light energy, what happens is an electron is promoted from its usual or ground state orbital to a higher energy orbital. The difference in energy between the two orbitals, the ground state and the excited state, is equal to the energy of the photon that caused the transition. In these cobalt compounds, the orbitals that are involved in absorbing the visible light are the d orbitals of the metal ion. Now, in a free transition metal, the d orbitals are all at the same energy, or they are degenerate. Remember that in a d subshell there are 5 d orbitals, and those are shown here on this diagram. They're all at the same height, implying that they all have the exact same relative energy, which is what degenerate means. Now, energy is going from top to bottom on this diagram, so low energy is at the bottom, higher energy is up here at the top. In the presence of an octahedral array of ligands, like we have in the two compounds that you synthesized, these 5 degenerate atomic orbitals get split into 2 groups. A couple of the orbitals move to a higher energy than the original energy of the orbitals. And then the remaining 3 orbitals shift to a lower energy. So now we have 2 sets of orbitals at different energies. If we have an electron in, let's say, the lower energy orbital right here, what can happen is that electron can absorb a photon, and if that photon has just the right energy, it can cause that electron to be promoted from this orbital, we'll erase it there, up to this orbital. Okay? So that transition will only happen if the incoming photon has an energy exactly equal to this energy gap. And the size of that energy gap there between the lower energy and higher energy d orbitals is called the crystal field splitting energy, or a delta O for octahedral. So our task is to understand why the hexamine compound would have a different crystal field splitting energy than the pentamine chloro compound. And crystal field theory also helps explain that, which we'll see on the next slide. After many experiments with many different complex ions with a variety of ligands, it became clear to chemists that there is a pattern to the size of the crystal field splitting energy caused by different ligands. Some ligands, like cobalt here and cyanide, are what we call strong field ligands. They tend to produce large crystal field splitting energies, and so those correspond to the blue end of the visible spectrum, and those are the short wavelengths. Other ligands down here at this end are what we call weak field ligands. They tend to produce a smaller crystal field splitting energy. A smaller energy would be in the red end of the visible spectrum, and those are longer wavelengths. So the compounds that we created were the hexamine cobalt complex. So that one would have had the formula CONH36, and the other one that we synthesized was the pentamine chloro, which was CONH35Cl, and this one was 3 plus, and this one was 2 plus. And what we saw with these compounds is that the hexamine compound was orange, meaning it absorbs in the blue region of the spectrum, about 450 to 500 nanometers wavelength. The rose compound absorbed at longer wavelengths in the yellow to green part of the spectrum, which would be lower in energy, which corresponds to the patterns that we see here. So that's crystal field theory, then, is what relates the structure of the complex ions in terms of what ligands they have to the wavelengths of light that they absorb. That's part of your assignment for this lab report, is to explain that in your own words. And it's also explained in writing in the Prelab section of your lab manual. This is the equation that is used to calculate the crystal field splitting energy, delta O, in kilojoules per mole. The crystal field splitting energy is equal to the energy of a mole of photons of whatever wavelength of light that corresponds to the lambda max for a given compound. And it's calculated by multiplying Hc over lambda, and I'll explain those terms in a second, times Avogadro's number, 6.02 times 10 to the 23rd photons in a mole, and then converting from joules to kilojoules by dividing by 1,000. In this first term here, Hc over lambda, H is Planck's constant, which is 6.626 times 10 to the minus 34th joules times seconds. C is the speed of light, which is 2.998 times 10 to the 8th meters per second. And lambda, or lambda max, is your wavelength. Now that lambda needs to be in meters, so you'll have to convert it from nanometers using the conversion factor that 1 times 10 to the 9th nanometers is equal to 1 meter. So you plug in HC and lambda, multiply by Avogadro's number, divide by 1,000, and you'll get your crystal field splitting energy. And you'll need to do that for each of the two compounds based on their 2 lambda maxes. When chemists carry out a synthesis reaction, it's common for them to calculate the theoretical and percent yield of their reaction. So we're going to do that for this experiment. To calculate the theoretical yield of a process, we first have to determine the limiting reactant, because that limits or determines the amount of product that can be formed. To identify the limiting reactant, we start by calculating the number of moles of each reactant used. Now, because my handwriting on this app tends to be slow, I went ahead and wrote these out ahead of time. This first equation here, grams times 1 mole over the molar mass, is the way you would set up the calculation to find the moles of the two solids that you used, the cobalt chloride hexahydrate and the ammonium chloride. One important thing to remember for the cobalt chloride hexahydrate is that the formula of the compound is COCl2.6H2O. So you have to include 1 cobalt, 2 chlorides, 12 hydrogens, and 6 oxygens, all in that molar mass. So that's for the two solids. To determine the number of moles of ammonia, you'll start with the milliliters of the ammonia solution that you used. You'll convert that to liters using 1 liter over 1,000 milliliters, and then convert that to moles of ammonia by using the conversion factor of the molarity, 15 moles of ammonia per 1 liter of solution. And that will give you the moles of ammonia that you used. To determine the moles of hydrogen peroxide that were used in the reaction, we're going to use the fact that the concentration was 30%, which is 30 grams of hydrogen peroxide in every 100 grams of solution. Now, we measured out the amount of solution in milliliters. So we'll start with the milliliters of solution. And we'll convert that to grams by multiplying by the density, which is 1.1 grams of solution for every 1 milliliter of the solution. Then we'll convert that to grams of hydrogen peroxide by using the concentration, 30 grams of actual H2O2 in every 100 grams of solution. I'm sorry, my handwriting is so atrocious on this. I'm just not very good at it yet. Fix that solution there. That should say solution. And finally, we'll convert that grams of hydrogen peroxide to moles by multiplying by 1 mole of H2O2 over the molar mass. Of H2O2. And that will give us moles of H2O2. So that's how we calculate the number of moles of each reactant. So once we have the moles of each of the substances, I would recommend starting with the moles of cobalt chloride hexahydrate and using the stoichiometer of the reaction, calculate the moles of the other reactants that are needed to completely react with it. So if you have enough moles of each of the other reactants, then cobalt chloride hexahydrate is your limiting reactant. I think that's probably what it is, but you'll need to do the calculation to be sure. And remember to include your stoichiometric ratios from the balanced equation, which are the coefficients, 2 to either 10 or 8 for ammonia and 1 for the hydrogen peroxide in your mole calculations. And then finally, using that limiting reactant, you can determine the theoretical yield by calculating the amount of product formed when all of the limiting reactant is consumed. And this is pretty easy because it's a 2-to-2 mole ratio, or 1-to-1. So however many moles of, if cobalt chloride hexahydrate is your limiting reactant, however many moles of cobalt chloride hexahydrate you used is how many moles of your complex ion product that you should get. Then you'd use the molar mass of that product to turn it into grams. And so that'll give you your theoretical yield of your product. Once you've calculated the theoretical yield, finding the percent yield is pretty simple. You'll use the equation shown here, where in the numerator you take the mass of product you actually obtained, or your actual yield, divided by the theoretical yield that you just calculated, times 100 to get units of percent. Now in this experiment, I'm not too concerned about the magnitude of your percent yield and your actual yield. They could be very small, they could even be a little over 100%, and that's okay. I mainly want to make sure that you know how to calculate theoretical and percent yield correctly. That concludes this video. I hope you found it helpful, and I'll see you in lab soon.